transmitter, the input will be between 0 to 100, and for 0 will be 3, and for 400 gallon per minute will be 15 psi G, and we call that as pneumatic transmitter. For pressure, the conversion will be from the pressure in mercury and then converted to current. So we call that as current transmitter. And for level, we have from level to voltage transmitter. I mean, the output will be in voltage, and for the concentration, the output will be in voltage as well. So as we all know, transmitter converts certain measured variable to one standard signal that is a function of in the function of measured variable, right? So when convert, okay, transmitter also converts the sensor output to a signal at certain input to a controller. For example, it is designed for specific type of sensor. So if flow rate, then we have this particular transmitter will only function for flow rate adjustment. Okay, so most commercial transmitter basically can adjust it based on their input range, or we call that span, okay, of that particular sensor. So given this, the type of transmitter here, we need to develop an expression for the output of each transmitter as a function of its input. Be sure to include appropriate unit. So if you notice here, meaning we have to develop for each, like for the flow rate transmitter, current transmitter, voltage transmitter, and also for the voltage transmitter. And it is already mentioned as a linear transmitter. So if you remember, we have the linear function for the transmitter. All right. All right. So we need to develop a linear function. So let's say, okay, so we have this. Let's look into the first flow rate one. So from here, we know the input is the gallon per minute for the first. We are talking about just this one. We're talking about just the first one. Okay, for this, the input will be so for 400 gallon per minute, it will be 15 pneumatic transmitter. So this will be output. All right, 15 psig. This is gallon per minute. And for 0 gallon per minute, the output will be 3 psig. Now, if you remember, it's a linear transmitter. So it has to be in terms of y equals to mx plus c. So the graph for the transmitter will be input and output. So it is actually output versus input. If you draw this graph, okay, from the output is in terms of PSIG. So from 3 and 15. 15 and 3, and the input will be 0 and 400. So at 400 PSIG, the input, the output will be 15 psig. For the 0 gallon per minute, the output will be the 3 PSIG. So if you plot, you will get a straight graph. Okay, linear expression. So here y equals to mx plus t. So the y here is the transmitter's function for the y is output. So PSIG equals to m, and the x here is the input. Okay, so it will be QM. It will be in Q gallon per minute plus the C. Okay, so this is QM, this is Q. All right. So now if we express this, we need to find out what is the uh, the the slope of this line. So the slope of this line can be calculated by finding the difference between y and x-axis. So that y will be 15 minus 3. X-axis is the 400 minus 0. This is m. Q plus c. The intersection at y-axis will be 3. PSIG. So basically the expression will be, if you simplify this, it will be 0.03 plus 3 PSIG. All right, so this is the unit. So if you want to put the unit also can, don't want to put also, still fine. So this is the general equation. Now from here, what we can tell? From this equation, we know the 0.03 is the gain for that particular transmitter. So this is pneumatic transmitter. So the gain for the pneumatic transmitter will be Km, which is equals to 0.03. Okay. The question asks us to develop an expression for the output of each transmitter as a function of input. So this is the expression. So this is the expression. And secondly, they ask us to calculate what is the gain of the transmitter. So the gain of the transmitter will be 0.03. Now from here, we can tell how to calculate the span and the zero. Because part B asking us to calculate the zero and the span. Okay, and is the gain constant or variable? So the span here can be calculated by finding the difference between the input. Okay, so this is basically the span. All right. So delta will be the difference, which is 400 minus 0. 400 gallon per minute is the span. Secondly, asking us to find out what is the zero. Zero is basically if you have a graph, okay, output versus input, and let's say the graph doesn't intersect. Okay, now the zero will be this portion. This is the zero that they mentioned. So from the graph, we can get the zero. If you notice, there is no indentation from the zero to the horizontal axis, right? So meaning here the zero doesn't exist. We don't have zero for this graph, but we have span for this graph. Okay. Now, second part, they're asking us to find out whether the gain is constant or variable. So the constant, the slope of the line is 0.03. As I extend this slope, the slope going to be same only for that linear line. So here the slope will be constant. Okay, this is an example for question number 1, pneumatic transmitter. Okay, the similar thing will be for all the transmitter given here, current transmitter, voltage and voltage transmitter. all you need to do, you need to find out which one is the input, which one is the output, and then plot output versus input graph, and from the output versus input graph come out with a linear equation, and from the linear equation find out what is the process gain, sorry, the transmitter gain, and from there from the graph we can find out what is the span and the zero. Okay, so I have shown an example for the first pneumatic transmitter. For the rest of the transmitter, make sure you try. Right. Now, second question. Define the level of accuracy and precision for each feature. Okay, we have three features. One, the point is very far. Second, far from the center, and second one is nearer to the center but far between each other, and the third one is very nearer to the center and nearer to each other. All right. Okay, so if you notice here, the first point here, okay, so if you notice the first figure here, the points are very nearer to each other but far from the center, and here very closer to the center and far from each other, and here close to each other and also close to the center. Now we need to define the level of accuracy and precision. So if you remember, the accuracy means how near it is to the target. So let's say my target is the center, how near it is. It is very far from the target. So for the first picture, how do we say the accuracy is low accuracy. Okay. Precision, talking about precision meaning how close is the point with each other. So if you notice, all these plots are closer to each other, so we can say it has high precision. Okay, now for the second figure, it is very close to the target, so we can say high accuracy. But talking about the distance between each point, it is low precision. And the last feature is very closer to each other and very closer to the target or the center. So we say that is high accuracy and high precision. Okay, so this is about question number 2. Now, question number 3. An engineer sets the pressure in supply tank using a very accurate manometer as a guide, and then reads the output of a 20 psig as in full scale. Pressure gauge attached to the tank as 10.2 psig. Sometimes later she repeats the procedure and obtains values of 10.4 and 10.3, meaning the reading from the pressure gauge is 10.2, 10.3 and 10.4. What can she say about the gauge precision, accuracy, resolution and repeatability? Okay, express these answers on the percentage of full scale. Okay, first let's talk about precision. What is precision meaning? Okay, they have given us 3 values, which is 10.2, 10.4 and 10.3. Now talking about precision meaning how close it is with each other. All right. So usually precision will be expressed in terms of standard deviation. Okay. Precision will be expressed in terms of standard deviation. Okay. So from all these 3 points, you need to find out what is the standard deviation for this particular point. So the standard deviation for this will be 0.1. Okay. Find out what is the mean, and then with the mean, you need to calculate what is the standard deviation. So the standard deviation will be 0.1. So using this 0.1, and the full scale of pressure is PSIG, 20 PSIG at full scale. So how we calculate, find out the percentage of full scale. Okay, we can get the percentage of full scale as 0.1 over the 20 PSIG. So this is standard deviation is PSIG because all these units are in PSIG. So this is PSIG over PSIG times with 100%. Okay, so this is to calculate percentage of full scale. So you will be getting 0.5% full scale. This is about precision. Secondly, they ask us to calculate about accuracy, how close it is to the target. Okay. Now, if you notice in the question, they didn't give us the true value of pressure. Okay, is not given. So without that true value, we cannot tell how close are these 3 points with the true values. So therefore, we cannot define accuracy at this point. Okay. Next is about resolution. Okay. Resolution meaning the smallest interval between two numerical values. Okay, so let's say we have 10.2 and 10.4. We need to find what is the interval between these two. Or we also can find out by measuring the highest and the difference between the highest and the lowest point. So from here, the resolution can be calculated by the percentage of the resolution can be calculated by, if you notice, 0.2, 0.3 and 4. So 10.2, 10.3 and 10.4. The difference is 0.1. So the percentage of resolution will be 0.1 PSIG over 20 PSIG times 100% will be 0.5% of resolution. And next, we need to find out the repeatability. Okay. Okay. The repeatability meaning how close, the repeatability meaning how close among a number of consecutive measurement of the output falls under the same operating condition, same equipment, single analysis, and also using the same input values for short time of period. So using all the same inputs, we'll be getting 10.2, 10.3, and 10.4. Okay, for the same value of input. So from here, the percentage of repeatability can be calculated by using plus minus 0.1 interval PSIG over 20 PSIG times 100%. So it will be plus minus 0.5% full scale. Okay, all the value we calculated just now for full scale. So full scale, 100%, so full scale. Okay, now here the answer is 0.05, meaning plus minus 0.05 with the original answer. Okay, that is question number 3. Now, question number 4. A temperature transducer has a range of 20 to 250 degrees Celsius. A measurement results in a value of 55 degrees Celsius for the temperature. We need to compare the errors if the accuracy is as provided below. Okay. So we need to also find out what is the possible temperature in each case. So let's move into with the accurate error of if the accuracy provided is 0.5 plus minus 0.5% at full scale. Okay. So how to do with this information? Okay. For 0 plus minus 0.5% full scale. So for the temperature transducer, their range is from 20 degrees Celsius to 250 degrees Celsius, meaning the 250 degrees Celsius is the full scale values. All right. So from here, we actually can know what is our span is. So the span is difference between the input. So 250 minus 20, which is 230 degree Celsius. Okay. All right. So using this, we need to calculate the error and the possible temperature. Correct. So with the 0.5% full scale, we can calculate the error by plus minus 0.5% accuracy that is given, and then 100% because of the full scale times with the full scale value. Okay, so this is plus minus 0.5 over 100%, and the full scale value is the 250 degree Celsius. Okay, so from here we will be getting plus minus 1.25 degree Celsius. So this is the error. So meaning the temperature, possible temperature in each case is actually the question is about the temperature at 55 degrees Celsius. So 55 degrees Celsius plus 1.25 degrees Celsius, or 55 degrees Celsius minus 1.25 degree Celsius. Okay, we have two values of temperature in this case. So this will be 53.25 degrees Celsius, and this will be 50, sorry, this is 56, and this is 53.275 degree Celsius. So we have two different temperature value. All right, this is part A. Part B is about 0.75% of span. So talking about 0.5% of span, the error is we need to calculate the accuracy. Sorry, we need to calculate the error if the accuracy is 0. Plus minus 0.75%. So instead of using 0.5%, we're going to use 0.75%. So here they are talking about, second part, they are talking about the span. So the span we already calculated as 230. So here we're going to put 230 degree Celsius, and this is 0.75, and we'll be calculating. Okay, so the way of calculation will be same for all part B and part C, similar to part A. So we can calculate the temperature, possible temperature in each case. So at the end of the day, end of the calculation, we'll be having plus minus what error, right? So with that error, we can plus minus with the 55 degree Celsius. Okay, you can try yourself. Now question number 5, a sensor resistance changes linearly from 100 to 180 ohm as temperature changes from 20 to 120 degree Celsius. Find the linear equation relating resistance and temperature and what is the zero and span. So if you notice, this is similar to our first question. So question number 5. Okay. So they are talking about a resistance, sensor resistance. Okay. So we know the sensor they are talking about here is the transmitter. Okay. And we have changes linearly from 100 to 180 ohm as temperatures change. So this is our input and this is our output. Okay, we need to find linear equation relating resistance and the temperature and find out what is the zero and span. So here the input, we can table that as per in our first question. So the input is 20 to 120 degrees Celsius. Output is 100 to 180. Okay, so from here we can plot for us to get the linear equation y equals to mx plus c. We need to plot first. Okay, this is output over input. Make sure you table so that you know which one is input and output. So at 20 and 120 input, at 20 this is 100 and 180, 100 and 180. So it's a linear, so it's a straight line. Okay, straight line. So from here we can calculate what is the transmitter's gain by finding the slope. So the slope can be calculated by finding the y-axis different divided with x-axis different, which is 80 divided 100 equals to 0.8 ohm over degree Celsius. Okay. Now, if you notice, the y-axis is the resistance and this is the temperature. So, the y equals to 0.8 ohm over degree Celsius, T degree Celsius plus the C, the y intersection. Okay, so we don't know what is the y intersection here. All right, so how are we going to calculate? Let's say I have my y as 180 and x as 120. What is my intersection will be the C. Okay, the y intersection will be. So by replacing that, I'll be getting my intersection as 84. So this is the linear equation. Now, second, we need to calculate what is the zero and span. The span is basically the difference between the input. Okay, so the span is 120 minus 20, which is 100 degree Celsius. Okay, talking about the zero, zero is the distance from here to the first point. So the zero here is basically distance from here to here, which is 20 degrees Celsius. So this is our span. This is about question number 5. Okay. Question number 6. We have a platinum resistance temperature detector. Okay. Measures resistance 100 ohm and 139.11 ohm at 0 and 100 degrees Celsius. So this is output and this is input. We need to find out what is the coefficient, temperature coefficient at 0 degrees Celsius, and this is about the uh, resistance temperature detector, RTD. So for this type of question, we cannot use the linear relationship that is provided here because it is already mentioned. It is not about the transmitter, it is about the detector. Okay, resistance temperature detector. Now, if you remember, we have the RTD equation as R at T temperature is equals to R at T naught temperature 1 plus the coefficient times with the temperature difference. Okay, so if you remember, the RT here is the resistance at temperature T, this is resistance at temperature T naught, and this is the temperature difference between the T and the T naught, and this is the coefficient, or we call that fractional change in resistance per degree of temperature at T naught. Okay, at T naught. All right. So the information given in the question, the input and output, right? The input will be 0 and 100 degrees Celsius, and the output will be 100 ohm and 139.11 ohm, right? Now, if you notice, this is the T naught, the 0, and this is the T. Okay, so by rearranging the equation, I actually will get the coefficient, temperature coefficient as in terms of R T naught. Just rearrange the equation. So this will be the temperature difference between these two. All right, divided the resistance difference between these two, divided with the temperature difference, which is T2 minus T1. So substituting all the value, I'll be getting the coefficient at T naught as 0.003911 per degree Celsius. Okay, this is the RTD coefficient. Now, question number 7 is similar to question number 6. Okay, in this case, the temperature coefficient is already provided at what temperature. Okay, so if resistance at temperature 20 is 106 ohm, we need to find out what is the resistance at 25 degree Celsius. Okay, so first we need to find out what is the resistance at this degree Celsius, 20 degrees Celsius, and then using the input and output values provided, we can calculate the resistance at 25 degree Celsius. Similar method, similar equation, because we are talking about RTD, resistance temperature detector. So we can use that method. So I'll skip this question. You can try yourself. Okay. Now question number 8, again about the resistance. Okay. Versus temperature. The value is given for the temperature and the resistance in the table. We need to find equation for the linear approximation of resistance between 100 and 100 degree Celsius. Okay, so I cannot extract this table, but Okay, good. All right. So we have this table here at particular temperature, or what we call that, at particular temperature, what is the resistance? So we basically need to find out the linear equation between using the resistance value between 100 and 130 degrees Celsius, meaning from here to here. All right. So if you know, so 100 to 130. So if you notice, the 100 here is the T1 and here 130 is the T2. All right. So using the RTD equation, using the temperature coefficient, the RT1 equals to, from here it is 573.4 and here RT2 is 605.52. Okay, so let's say we are talking about this range, right? So let's assume 105 as the T naught. If 105 is 115 is the T naught, the RT naught is 589.48. Okay, so we can use this equation to calculate the temperature coefficient first, which we already derived earlier using the RTD equation. T2 minus T1. So substituting this value, we'll be getting all these values. RT0 we have ready, R2 we have, R1 we have, T2 we have, T1 we have, RT0 we have. So the temperature coefficient is actually 0.0018 per degree Celsius. Okay, so this is about temperature coefficient, but the question asking us to find out the linear equation, right? So the linear equation can be written as RT is RT naught 1 plus temperature coefficient delta T. So the RT naught here is 589.48 ohm. All right, 1 plus the temperature coefficient is 0.0018 per degree Celsius, and the T here is the difference between T and 115. All right, so this is about the linear equation. All right, so part next, we need to, actually the question, this one is this portion, the B is actually for A. You need to assume the T naught as 105. Okay, so the part B, part C is actually part B. So we need to find out what is the resistance at 105. So substituting in this equation, resistance at temperature 105 degrees Celsius is what? We have this coefficient ready. This value we have, we need to find out the T, which is 105. Okay, substituting here, we'll be getting the resistance at 578.87 ohm. Okay, this is the question number 8 is about. All right. Okay. We have a J-type thermocouples that measures 22.500 milliwatt, okay, with a 0 degree Celsius reference junction. Calculate the junction temperature. Okay, what is the junction temperature will be? All right. So before we start, we come out with the voltage equation first. The true voltage is actually equals to transmitter voltage plus the V reference junction. Okay. So here the VM is, we don't know what is that, but V reference is actually V at T equals to 0 degrees Celsius, which is also equals to 0. So here the Vm plus 0. V true is Vm plus 0. So technically the V true become Vm. Okay. So in the question, the value given here is 22.5. So the V true here is 22.5 milliwatt. Okay. We need to calculate the junction temperature. So before starting with the junction temperature, we need to know what is the V corrected. Okay. The V corrected here is the V true, which is 22.5 milliwatt. Okay. The T junction can be calculated by finding the interpolation. For example, go to, this is J type thermocouple. Okay. Go to J type thermocouple. Okay. J type thermocouple. 22.5 falls at 22.5. Here. 22.5 falls between the 22.455 and 22.510. Okay. Now, how to read the temperature for this 4.1, but then it falls here, right? The temperature for this value, 22.455, is actually 410 plus 1. So this is actually 411. And for the 22.51, it is 410 plus 2. So it is actually 412. So these values can be calculated. Okay, T and the milliwatt interpolation. So at 411 degrees Celsius, the milliwatt is 22.455. And at 412 degrees Celsius, the milliwatt is 22.510. But here our true value is 22.5. So what is the T here? The T junction here. So the interpolation of T junction will give 411.818 degree Celsius. And the question asking us to calculate junction temperature. Okay, so that is the T junction or junction temperature that we calculated. Now for question number 10, instead of using J-type thermocouple, now they are using K-type thermocouple with 0% reference junction. We monitor an oven temperature at about 306.34 degrees Celsius. So we need to calculate the corrected milliwatt reading. Okay. So for that corrected milliwatt reading, we know here the T reference here is already given as 0 degrees Celsius. So at T reference, the V reference will be 0. Our V true is basically Vm plus V reference, right? So here the V reference is 0, meaning the V true is equals to VM. Okay, the V true here is at corrected. How to say the V true here is the corrected V, meaning at T junction. Okay, so the T junction given here is the 306.34 degrees Celsius. Earlier we calculated T junction. Now T junction is given. So this is about K-type thermocouple. So go to K-type thermocouple with 306 306 and 307. Our value is 306.34. So it falls between 12.457 milliwatt and 12.499 milliwatt. So we still need to perform the interpolation. So at 306 and 306.34 and 307. So at 306, the milliwatt is 12.457. And here, the V true is the one that we are finding. And here, this is 12.499. So from here, we can get the V true by doing the interpolation. We'll be getting 12.47128 milliwatt. Or you can equate that as 12.47 milliwatt. Okay, this is about type K. And the last question is about J-type thermocouple is used to measure 500 degrees Celsius with 100 degrees Celsius reference. Calculate the measured voltage. Okay, so same method, but here we have V true equals to Vm plus V reference. So the V true here, before that Vm plus V reference. Okay, so the temperature is given for temperature reference that is given is negative 10 degree Celsius. So at negative 10 degrees Celsius, V reference will be negative 0.501. This is a J type thermocouple. Okay, J type thermocouple at negative 10 degrees Celsius, 0 plus negative 10. So negative 10, the value will be negative 501. So that is why the V reference will be negative 0.501. Now the T junction here is the value given as 500 degree Celsius. So at 500 degrees Celsius, at 500 degrees Celsius, okay, the milliwatt will be 27.393. 20, the V true will be 27.393. All right. Substituting here in this equation, so 27.393 equals to Vm plus V reference is the negative 0.501. My Vm will be 27.894 milliwatt. We need to calculate the measured voltage. Okay, Vm. So Vm is already calculated as shown here. So this is about our question number 11. Okay, so that is about today's session. today's tutorial session. Any question you can ask me. Okay, no question. You can leave your name in the chat session now, and we can end the session. So all the best for your final. See you all